Images from NASA's discovery of Callisto. Through Voyager, Callisto, Calliope, Betelgeuse, and the neon moons, we're a slow-burning melody, but we'll land soon. This is one of the lines from Coldplay's new song Coloratura. We all know that music brings people together, and Coldplay excels at this. Their fascinating and inspiring connections to space exploration missions, celestial objects, and stars are so subtle. It's as though they're driving us towards the future, when mankind will ideally be a part of something bigger. Perhaps a future in which interstellar travel is possible. There are references to Voyager, the famous NASA spacecraft that escaped the solar system and was the first human-made mission to do so, as well as Calliope and Betelgeuse. Calliope is an asteroid discovered in our solar system's asteroid belt in 1852, and Betelgeuse is a star in the Orion constellation that will go supernova, but we don't know when. We'd like to talk about Callisto today. This concludes our magnificent tour to Jupiter's 4 moons, the Galilean satellites. Follow me to learn more about Jupiter's second biggest moon. So far, we've had the opportunity to better comprehend the chemical, physical, and dynamical properties of Ganymede, Europa, and Io, 3 of the 4 Galilean satellites, and earlier movies. Each of them has distinct characteristics that distinguish it as a distinct moon. Europa has freckles on its surface, Io has volcanoes that spew sulfur and sulfur dioxide plumes, and Ganymede has an ocean of liquid water beneath its frozen crust. So, how about Callisto? First and foremost, where does the name Callisto come from? You should know that Zeus had numerous lovers, according to Greek mythology. One of them was Callisto. She was a nymph, a beautiful being affiliated with Artemis, the goddess of hunting. The name was proposed again by astronomer Simon Marius, although it was not widely used until the mid-20th century. Previously, he was known by his own designation, Jupiter 5, or the 4th satellite of Jupiter. From a cultural standpoint, the origin of names is critical. When it comes to astronomy and astrophysics, though, we require something more. We want to have Callisto's whole identity card. We'd like to know, for example, how far it is from Jupiter. Callisto is the most distant of Jupiter's 4 Galilean moons, as of today. It is orbiting the gaseous planet at a distance of 1,880,000 kilometers. This is a massive distance, over 26 times larger than Jupiter's radius. We observed in the films about Europa, Io, and Ganymede that they all have some form of resonance, which means that their orbits are precisely coupled. These orbit resonances are tying the satellites together, and the tidal locking phenomena causes some internal structure mechanisms that may contribute to the heating of the moon's interior. Callisto, on the other hand, is so far away from the other 3 moons that it does not participate in the mean motion resonance. A considerable distance from the planet also entails a long orbital period, which lasts around 16.7 Earth days because Callisto must travel a long distance before terminating a whole orbit. Throughout the years, we had missions that encountered Callisto, producing magnificent photos and gathering valuable data for us. We'll talk about it later in the video, and I'll show you the incredible photos I promised. But first, it is important to note that all of these trips have helped us better grasp the physical and chemical features of the moon. For example, we know that Callisto has an average density of 1.83 grams per centimeter cubed. If you assume that the density of water is 1 gram per centimeter cubed, Callisto is denser than water on average. This indicates that it is composed of stony material and water ice, along with certain volatile ices such as ammonia. How do we know Callisto is composed of water ice? It all comes down to spectroscopy. When astronomers examined the moon with near-infrared filters, they discovered ice absorption bands, indicating the presence of ice. This, however, is not the end of the narrative. More precise measurements show that ice water is common on its surface. When it comes to the surface, we know that Callisto is asymmetric, with the leading hemisphere being darker than the trailing one. This is unusual because Europa, Io, and Ganymede are the opposite. But we have a lot more information about Callisto. We can infer some internal features, for example, from gravity field and magnetic field observations. We discovered that Callisto has a radius of 2,403 kilometers, which is bigger than the radius of our moon, and that its interior contains a pretty homogeneous mixture of equivalent amounts of ice and rocks. The surface layer may differ from the underlying ice rock layer in a number of ways, such as the percentage of rock it contains. Because there are no orbital resonances with other moons, and hence no tidal heating, Callisto's geological history is more simpler than Ganymede's, despite the fact that the two moons are extremely similar in bulk attributes. We believe Callisto has never been sufficiently hot to melt its ice component. This is not to say that there isn't an ocean of liquid water in its interior. This is owing to the unusual behavior of ice melting temperature, which drops as pressure increases. This crucial temperature is achieved between 100 and 200 kilometers. Furthermore, the presence of a small amount of ammonia essentially guarantees the existence of the liquid because ammonia has the magical ability to lower the melting temperature even further. The most intriguing aspect is the possibility of life in Callisto's subterranean ocean. A hypothetical underground ocean could be made out of salt water. Some organisms, such as halophiles, may be able to thrive in that ocean. Extremophiles are organisms that thrive under high salt concentrations. Perfect, I believe I told you a lot about Callisto. Now it's time to talk about the exploration missions that provided us with this massive amount of information and to see the actual photographs NASA shot of this amazing moon. The Pioneer mission is the starting point for Callisto's explorations. Pioneer 10 and 11 were two spacecraft that arrived at Jupiter in the early 1970s but added little new information about Callisto to what was already known from Earth-based observations. The major breakthrough came in 1979 with the arrival of the Voyager 1 and Voyager 2 flybys. The two spacecraft, whose goal was to leave the solar system, flew close to the moon and imaged more than half of its surface with a resolution of 1 to 2 kilometers. They also took measurements of mass, temperature, and form. Voyager 1 captured this image of Callisto on March 6, 1979, as it approached Jupiter's outer big satellite. The spacecraft was 350,000 kilometers away from Callisto at the time, and the surface features are around 7 kilometers across. The notable bullseye feature in this image is thought to be a massive impact basin, akin to Mare Orientale on Earth. The brighter circular point spans around 600 kilometers, whereas the outer ring spans roughly 2,600 kilometers. This is the first identified basin in the Jovian system and supports the idea of Callisto having an ancient surface. Callisto's darker color, about half as reflective as Ganymede but still twice as bright as our moon, suggested that its upper surface was a dirty ice or water-rich rock frozen at Callisto's cold surface, with an equatorial temperature of about 120 Kelvin or 243 degrees Fahrenheit. We had to wait until 1995 for a second phase of investigation after Voyager's interactions with Callisto. The Galileo spacecraft passed it 8 times between 1994 and 2001, the last time at a distance of 138 kilometers from the surface. The Galileo orbiter captured stunning images of Callisto. As previously stated, Voyager has a resolution of 1 to 2 kilometers. However, Galileo provided a handful of images with resolutions as high as 15 meters of selected portions of the surface. The Galileo spacecraft's high-resolution near-infrared and UV spectra have shown a variety of non-ice minerals, including magnesium silicates and possibly ammonia and organic molecules. Of course, there are some images from Galileo. For example, this one has brilliant scars on a darker surface, indicating a long history of impacts on Jupiter's moon. According to NASA, the image, taken in May 2001, is the only complete global color image of Callisto obtained by Galileo, which has been orbiting Jupiter since December 1995. The surface of Callisto is consistently cratered but not homogeneous in color or brightness. The brighter parts, according to scientists, are mostly ice, whereas the darker areas are highly degraded ice core debris. These four views of Jupiter's second largest moon, Callisto, show how increasing resolution allows for surface interpretation. The surface is shown to have many little bright spots in the global view, top left, but the larger craters are revealed in the regional view, top right. The local view, bottom right, reveals not only tiny craters and the precise structure of bigger craters, but also a smooth dark covering of material that appears to cover much of the surface. In this highest resolution view of Callisto's surface, 30 meters per picture element, the close-up shot, bottom left, reveals a remarkable smoothness. Isn't it incredible that we have such high-resolution images of other things in our solar system? Last but not least, on its way to Saturn in 2000, the Cassini spacecraft obtained high-quality infrared spectra of the Galilean satellites, including Callisto. It obtained high-resolution infrared spectra of Galilean satellites. On its approach to Pluto, a New Horizon probe captured new photos and spectra of Callisto. Before we conclude this movie, we'd like to point you that NASA did a conceptual study dubbed HOPE, which stands for Human Outer Planets Exploration, in 2003. This was about the future of human exploration of the outer solar system, and the target chosen for detailed consideration was Callisto. NASA indicated in December 2003 that a manned journey to Callisto could be conceivable in the 2040s. Building a base on Callisto could allow for remote exploration of Europa, or it could be a perfect place for a Jovian system way station servicing spacecraft traveling further into the outer solar system, receiving gravitational assistance from a close flyby of Jupiter after leaving its moon.